We know that unsupervised machine learning is cool, I guess, and we need to now learn how do you go about implementing it. Let's see how you would go about doing that. We have already seen one application over, where we were using the same example as a classification example, but now I've tweaked it a little and said this is clustering. Over here, assume that you are not given any prior information on which movie a user likes or dislikes. And your unsupervised machine learning algorithm has now come up with two patterns in the data. It saw these two features. On the x-axis, we have the movie time, and on the y-axis, it was IMDb rating. Your unsupervised machine learning algorithm saw this data set and said that, you know what, I think this set over here is similar, and this set over here is similar. Okay. So it still doesn't know whether these are the movie that the user likes and these are the movie that it doesn't like. It doesn't know that. Okay, it's not its job to know that. The only thing it did is, it created these two clusters for us. So now my task is, how do you go about doing something like this? Let's say you are given this data set like this, everything is black. Now your job is to color some of these as red, some of these as green. Okay. And to do that, intuitively in your mind, you can obviously look at these two things and say, okay, these are red and these are green. So, but what did you use intuitively in your mind right now to color those two segments out, or cluster those two things? So what do we need for clustering? So distance from other points is important, right? So the first thing that we need is some way to measure the proximity of these points. So the first thing that we need is, to do these implement clustering algorithm, we need to have some sort of proximity measure. And have we studied any proximity measures already in this class? Yep, Euclidean distance. What was the other one that we have done? So Euclidean distance will measure the magnitude of the vectors. It will measure how far apart in the Euclidean space you are. Another way to look at it is also by looking at something called as a Manhattan distance. Have you guys heard of it? It's also called city block distance, or no, you can look it up. Just another way of coming up with how far you are. And you could also use something like cosine distance. Most likely it won't be used, you won't come across for clustering applications, even though there might be some cases where the things which are apart in angular distances, you want to get a sense of those things. So cosine distances are the other one. If you haven't seen our previous class on where we talk about Euclidean distances and cosine distances, please have a look at those videos as well. Okay. How do you go about calculating the Euclidean distance? I want to calculate the Euclidean distance between this point and this point. So what would you do? It's this d over here, right? It's simply root of x1 minus x2 the whole square plus y1 minus y2 the whole square, right? Just subtract the x coordinates, y coordinates, just use Pythagoras theorem over here, and you could imagine a triangle over here. You can get Euclidean distance with that. That you also need is, let's say you calculate Euclidean distances, and you say that, what, these points are, I think that these are close, these are close. The second thing that you also need is, once you create your cluster, what you also need to know what a good cluster looks like, right? And there are some measures that see how close apart these points are, or how far these two clusters are. And based on the evaluation criteria that you use, your problem or at hand, or your algorithm that you'll choose, you will tweak that a little as well. So that's like a bigger picture, right? That's how you would approach this problem. But today we are going to study about one such specific approach to clustering, which is called as k-means, and it's by far one of the most popular algorithms for clustering. So we are going to go about in depth in how k-means goes about finding those clusters. At a high level, we know that we need two things. The first one is a distance measure, which we could use as a Euclidean distance, a Manhattan distance, or maybe even cosine distances, right? And the second one is you need some sort of evaluation criteria, right? So you need some sort of evaluation criteria to look at those clusters and see whether you have got a good cluster or not. So keep these two things in mind as we go ahead. So this is how the k-means works. Let's imagine that we have the same data set as you saw before, okay? And you are given this set of points. Now these points are not labeled. These visually they look separate, and you know that now eventually you should come up with an answer which has all these points grouped together and all these points grouped together. Can someone tell me if you have heard of any other iterative methods from our previous classes, or no, if you might have studied machine learning or any other algorithm that you have seen somewhere else? What are some examples of an iterative algorithm? Yep, gradient descent, bisection, these are uh, iterative algorithms, right? If you have studied searching and sorting as well, so you try to sort things, those are iterative algorithms, right? They perform iterations on your data set, and you eventually come up with a good answer. So k-means, the reason why it is called k-means that it comes with k centroids of the cluster. Over here, by looking at the data, we knew that there were only 2 clusters. So let's say we assume that we start with k is equal to 2. So we have 2 crosses over here. These crosses are also called as centroids of that cluster. Okay. So right now we are saying that our cluster is at this point, around this. Okay, at this point in the algorithm, we are just saying that our cluster is just at this point, this x over here. So we are saying that this is where these 2 clusters are. And how did we come to this point? Randomly. We just select 2 points at random, and how you choose those points are also critical. We'll come to that in a minute, but that will also affect performance of your algorithm. So let's say you come over here and you initialize these 2 crosses or these 2 centroids randomly at your point. Okay, so what k-means is going to do next is it is trying to find the distance from all these points to these clusters. Okay, so it will calculate the distance between this white point with this red x, all the blue points with each of these points. Okay, so you will calculate distance from all these points. And what it says is, given the points which are closest to these red cross over here, the red centroid over here, color all of them with red. And when I say color all of them with red, it means like assign this cluster 1 or the cluster red to all these points. So all these points right now are in our red cluster, and all these points are in our blue cluster. So it saw that every point asks itself, where am I closest to? Am I close to red or am I close to blue? And this point said, I'm close to red, I'm close to red, I'm close to red. So it marked itself as red. Okay. And similarly for all these points, they said, where am I closest to? Am I close to blue or red? And they'll mark themselves as red or blue. Okay. And again, this is called the assignment step, because each point is being assigned to a particular cluster over here right now. Okay. In the next step, what k-means does is, okay, once this assignment is complete, let's see what do we have in red. So it collects all the points which are in red now. Then it asks itself, okay, once I know these are all red points, what is the mean of all these points? So it says, okay, the mean is somewhere over here. The next step, what it is going to do is, now that it knows that the mean is over here, it is going to move this x to that position. Okay, so it is trying to get close to where the k is trying to get close to the mean over here, right? K means, I guess that's how they came up with the k and the mean, right? So the k is, the centroid is trying to come up to this mean location over here. So now he's asking, what happens if you come up with the point over here which is equidistant from red and x? Well, in that case, when you are implementing an algorithm, you will have to either just select one or the other. Okay, so let's say you're trying to implement it, your exact lines of statement or the pseudocode would look something like this. It is going to say, if I'm closest to red, or no, if the distance from red is greater than or equal to something, or no, if distance is greater than something, do this. If distance is less than something, do this. Else, just assign myself to blue. Okay, so you just have a third condition over there saying that, which catches all. So in the equality case, so you just randomly assign yourself to one cluster if you are equidistant. Right, so our x moved to this point. Okay, Now blue is going to do the same. It is going to calculate the mean of all the blue points, and then it is going to move its centroid to that location over there. So blue moved itself to a location which was the mean of all its points. Okay. So now at this point, this is the scenario that we have. Now there are some red crosses over here. There are some blues over here. So now let's see what happens. All points right now are going to calculate, ask the question to themselves again. Am I close to red or am I close to blue? Am I close to red or am I close to blue? Right? So each point is going to ask itself the same question again. And based on where it is closest to, they will color themselves as red or blue. In this case, what happened was these points ended up being close to this blue, and this red cross being is closest to all these red points. So these points assign themselves to the red cluster. And you do the same step again. Okay, so what you're going to see is eventually you will come up with something like this. Your red cross moved to this point because that's where most red points are. Your blue cross moved inside over there, and because that's where all your blue points are. But there is just one point which is mislabeled over here, and there are these 3 points over here. Next time when they ask this question to themselves, where am I closest to, they'll end up falling in the right cluster again. So you end up with something like this, wherein after a point, what is going to happen is your X over here is not going to move enough, okay, because there is no space to move. Or every time anything happens, each point says that I'm in the same cluster, so nothing happens, and your X or the centroid stop moving after a point. So you eventually will converge. But my question to you is, and I already given a hint to you guys, we have seen in gradient descent that always you don't end up with a correct answer over there. What's the correct answer? You don't end up with the best possible solution to the given problem, right? So there are some local minimas. What do you think is the case with k-means? Will it always end up classifying these clusters perfectly? Let me go back over here. What if the choice gets selected in the wrong cluster? So no, you are saying that no, it won't end up with the right answer always. And this choice over here, what we are saying is no, that is certain that whoever is closest to that point will assign itself. But yeah, all of you have the intuition correct over there that no, it's not going to always end up with the right answer over there, and we'll see why. So I have a question for you. The distortion of a cluster is given by this formula below. Calculate the distortion of clustering algorithm with the following values. Okay, so you are given this cluster over here. Okay, and at this point, this has converged. Okay, now your X is not moving anymore. But the distortion, or how well we have did in this clustering algorithm, is given by the distance between the centroid and each of these points. How closely we have been able to estimate a cluster properly will be given by this formula over here, which is for the distortion of that particular cluster. So go ahead and calculate the distortion for that. Guys, it is pretty straightforward. You just have to square the differences between each of the X and the X over here, right? And just square them up and then add all of that together. Let me answer Grusha's question. We took 2 centroids initially over here, but we didn't know that the data will have 2 clusters, right? So the choice of K is totally up to you, okay? And we are going to see in next 1 or 2 slides, how do you go about deciding how many centroids to take. Over here we are, just to explain you, I just said, what, let's say we take 2 centroids or 2 clusters, but by even looking at the data, you knew that there were only 2 clusters. But how about when you are in higher dimensions, like when you have like 1000 features, you can't even visualize that, right? But the approach is going to be the same. You start with let's say a number of clusters between, let's say, 3 and 10, and then you see for what kind of clusters you are getting good results. Okay, and what do you mean by result is the distortion, right? The distortion measure is going to give you how well you did with your clustering. So we are going to look at our distortion for different number of clusters, and based on where we get good results, we are going to select the number of K or number of centroids or the number of clusters. Yeah, over here, if you would have started with 3 over here, right? So you would end up with 3 clusters, which will not be optimum, right? So you will end up with the value of distortion, which will be much higher, or in some cases, it won't be that good. Yep, if the distortion is less, that means better the result. So it's, again, it's just one of the parameters, or no, one way to look at how well we did. Okay, it's not just the only way that you could look at, but looking at the distortion, you can say how well your clustering algorithm performed. Okay, answer over there, which is 7, right? So that's how you would go about calculating it. You just take a difference between all these points over there. So on the second point, there is no error, right? So 3,3 and 3,3, there is no distance between that. So that's 0. Now on the third one, you have 2 minus 3 the whole square, and again 2 minus 3 the whole square. So the total will come up to 7. Okay. So coming to Grusha's question, how do we go about selecting the number of clusters, right? And the answer to that is you don't know at start, know what the right number of Ks. So you start off with something, let's say you start off with one number of cluster as 1 over here, and you see that the distortion is 3.5. So you say, okay, let me do K means once more. You say number of clusters as 2, and you say distortion is something, it's around 1.5 or 1.7. And after a point, you reach to a point where now you get this elbow-like structure. So imagine like this is your shoulder, and this is your elbow, and maybe this is your arm somewhere, right? And this is your hand over here, right? So what you do is, you select a point which is at this elbow location, which is around 3. And the reason for that is after this, you are just getting some incrementally better results, right? So you're not getting significant improvement in your distortion. So it doesn't make sense to do these many iterations from a computation standpoint, right? Because remember, even though k-means as a whole it's efficient, but if you have so many data points, the number of iterations do matter. So after a point, you say that, you know what, I'm just going to get incrementally better results, so it doesn't make more sense. Over here, what we are seeing is what we call as the elbow method to determine how many number of clusters we should choose, right? So on the x-axis, we have the k, which is the number of clusters that we are selecting. Okay, and on the y-axis, we have the distortion. How did we come up with the distortion? We just calculated, right? So you guys know how to calculate distortion. You start off saying that, okay, let me start with k as 1. And how much distortion do I have? I have 3.5. And let's say for 2, how much do I have? Around 1.7. Around 3, I have around 1, right? You look at this graph and say that, you know what, this part after 3, I'm just getting incrementally better results. So there is no point in me choosing more than 4 or 5 clusters. So I'm going to choose this point in this structure, which looks like an elbow, and I'm going to choose this point, which is 3. And that's how you would go about determining how many clusters you should use for your k-means clustering. Questions is, so convergence depends on k. Okay, so that's my question to you. I already asked this question to you guys, and you said that no, you don't always converge to the right answer or the best possible solution, right? Let's say you end up with a situation like this, and in the previous one, I did cheat and say that, you know what, this blue point is closest to this red point, but even by looking at it, it is actually not that close, right? So it is more close to blue point over here. So let's say now your x's stop moving at this point. So what's going to happen? You're eventually going to end up saying that this is the right cluster, right? So you're going to cluster it like this. By looking at it, you're going to end up with a lot more distortion, even though you should have ended up with optimal number of k as 2, but still your distortion is going to be very large, right? Because distances from each of these points to this x is going to be very high, right? So again, I have told this answer to you, but my question to you is, what factor will determine, will we converge to these 2 clusters or not? What is one critical step that we take which will determine, will we just forget about anything in general, just for this particular example? We know that the optimal number of clusters is 2 by just looking at the data, right? We selected k is equal to 2, but we still ended up with a situation like this where the x's are not moving anymore. So what led to this situation? How did we end up over here? And what will determine if you are going to end up in this situation? Again, I'm going to go back over here and I'm going to go through all the steps, and you need to tell me which step is the most critical. Okay. So yeah, that's one complete loop. So out of these three things, 1, 2, and 3, what is determining factor which will affect our convergence? You have 3 choices. Okay, this is the first choice, second choice, and this was the third choice. So Sanway says occurrence of a point near to a centroid, second choice. That is, the second one is not the correct answer, and Grusha got that one right. The first one, which is the most critical one, where do we start, right? So we are starting randomly at this, in this space over here. Based on where we start, we're going to end up with different solution, and depending on where we initialize these centroids, we are going to end up with different solutions. So it is very, I would say, biased towards your initial locations. Okay. So one approach to know what you do is, a lot of people use an approach where they would initialize these centroids right on the top of one of these points in this data point. Okay, so either you would start this red over here on this point and a blue on some other point. So you'll just place them randomly onto the point itself. But again, there is no guarantee that you will end up with an optimal solution. So what's another problem with k-means? We have already seen this before. If someone would have given you this data and imagine that everything is same colored, so what were the 2 clusters that you would have given out just by looking at the data? Yeah, Krishna got that right. Inner circle and the outer circle, right? But this is what k-means is giving it. K-means is saying that segment it like this, which is definitely not the optimal solution for this case. The reason is, k-means doesn't work with the data set which is not linearly separable. So in this one, it is not linearly separable, and thus we are ending up with a solution that k-means is giving us. In our last classifier that we studied, which was SVM classifier, we had that kernel method that we were applying to make it work with in the nonlinear case. So if you want to try out something like that, can you apply a nonlinear kernel to that data and then apply k-means? Does it work after that? Tell me if that works. Okay. And it is also sensitive to outliers. So in this case over here, forget about these lines which are drawn, right? And you were to come up with 2 clusters. So Grusha, your answer to your question is just by looking at the data and knowing the domain itself, right? And that's what makes machine learning difficult. Otherwise, everyone would have just taken the data and applied it to the methods which are available in scikit-learn and got great results, right? But the reason why machine learning in practice, so understanding it, learning it is not difficult. Okay, don't get me wrong. I always tell our friends, I always tell all our students that learning machine learning is not difficult. Applying machine learning is. So just by the only way to come up with saying that whether the data is linearly separable or not is either having some domain knowledge about it and either visualizing it. And how much would you visualize, right? Either you could visualize in 2 dimensions, right? What is your data has more than a million features? Quite possible, right? So what do you do in those cases? You don't know that always. So coming to this point over here, the optimal clusters over here would have been the cluster 1 over here and cluster 2 over here, right? Or maybe if you want, you can take this point over here as well and cluster 2 over here. But what k-means ended up doing was, it created 2 clusters like this because maybe the centroid started here somewhere and it got stuck after that point. It couldn't move anymore. So it created these 2 clusters like this one, which was not an optimal solution. So k-means is also prone to the outliers over there. One way to get rid of it is to first visualize or first inspect your data, go over it, and if there are any points with which have very high variance, you just get rid of them before applying your k-means. Okay.